Is anybody in their need of a beer, or can you bear with me a few more minutes? Okay, so I have some live demo I can also do. I'll try to keep it as short as possible, so maybe we can do a bit more of demo, or maybe I can also demo after while you guys are holding a beer, and maybe me as well. I would prefer that. So Adrian unfortunately couldn't make it today, so I will speak and talk about our joint work. Adrian started this a bit earlier than I, especially on the simulation part. When we heard problems about simulation performance in the previous talk, this has been our main focus for the last 4 years. So we do compute everything in parallel, and it's on the GPU, and it's highly efficient, because we early on realized reinforcement learning will not work if we cannot speed up things. So I will hopefully be able to show you some of that stuff. So the talk is actually about something very simple. So it's just about how to overtake other agents. And as you saw with cars, there is problems there too, but most of you might have driven a car, and you know you don't have to plan ahead your overtaking for very far. If the situation allows, you can overtake and keep the speed you want. So this is very simple. Safety rules apply. The environment is kind of made for cars to overtake each other. Now if you look outside for the railway, we made it a bit more complicated, and this is also due to the cost of our infrastructure. So now the same problem of overtaking, but on tracks, becomes a planning problem. So you have to think ahead. When can I actually overtake? So how your traffic flows doesn't only depend on your situation now, but you have to look into the future. And one of the reasons is because these switches are very expensive. So I mean, we could put a lot of switches in, and then you can overtake whenever you like, but that will increase the prices of the tickets and public transport in general, so I think people would not be happy. So how do we now optimize this? This is the question, how we can do this in the outside world. And again, the problem still will be very simple, because there's not many decisions you can actually take. There's only decisions at switches that are important. Decisions when the train is just running on a straight track is not so important. You can brake, of course, but you cannot change anything there. At the switch, you can take binary decisions. So coming from one side to a switch, you can choose if you want to reroute your train. For obvious reasons, we need these because we want the trains to not only run from one point to the next, but we want to connect all the train stations within Switzerland. So that's one reason. And the other reason is that we sometimes want to reorder trains. So we have to maybe put a train on a side track such that a faster train can pass, or a more important train can pass first. So that's one of the binary decisions you can make at the switch. But then of course you can also come to a switch from the other side, and now you can again make a binary decision, because there might be several trains arriving at the switch. So now you can choose which train should pass the switch first. For this I think we have 32,000 signals outside that we use for managing this traffic. So you just set the green light. For example, this example, you take the fast train first, and you take the slower freight train behind. So once you've made that decision, you have to wait till the next decision point till you can reorder your decision. So if you make mistakes, they will actually have influence into your future. So this is quite a hard problem. Now, coming from just binary decisions on different sides of switches, the complexity of the problem grows rapidly. So if you look at this train and you want to route it through this simple area of railway network, you will have approximately 30 options, so 30 possible paths you can take. What do you think happens if I add another train and we want to route 2 trains through that system and to order them? Do you have any ideas how many possibilities I have? Any guesses?
2 power 30.
Yeah, 900.
900, very good guess. So then you can probably guess what happens with 4. We go up to 8 million, and then we quickly go above the possibilities of number of atoms in the observed universe. And this is just 80 trains on this little thing here. And if you look outside, we probably already see almost 80 trains just looking around. So we have much more trains and much bigger network. So the number is just astronomical. There's no way you can find the optimal solution just by trying all the different combinations. So how do we do it? Because you realize if you come by train to work that most times we are on time. So somehow we manage to handle this huge number of possibilities. So the way this was done in the early days was the system which was much easier. We had a very sparse network. We had many people working on small areas of the railway network, so humans just communicated and you can kind of find an optimal solution for those stages. But if you look at today, the network has become much larger, and now we had to divide the network into groups. In Switzerland, it's actually 5 areas where we have operations center where we manage traffic, and these 5 areas actually manage traffic more or less independently. Their connection is mostly phone lines, so they are talking to each other when they need to optimize across. We have computer systems aiding them, especially because our decisions will have impacts in the future. We have systems that predict what will traffic look like in the future if it goes on like this. So we do kind of simulation into the future, given the current situation, what will it look like in half an hour? Are there actions that need to be taken? So this is what we see today. Now if you look at the behavior of humans, especially in the Western world, the mobility starts growing a lot. So projections show that in areas like Zurich we will have about 40% more passengers on the network coming in a few years. So somehow we're going to need to put more traffic on the network outside and still maintain stable traffic. And now we can not only look at separate regions, because when you make the system more dense, it becomes more unstable as well. So any disturbance you get in your train traffic system will propagate along your system. So once something messes up in Zurich and you have very tight traffic all over Switzerland, this will influence other areas of Switzerland. So somehow we cannot optimize regions anymore, we have to optimize all of Switzerland, and we have to do this faster than we do today. So this is the question, and this is the research we are doing for the last few years, is to figure out this question mark. So what kind of supporting systems can we generate to solve this problem? We started by wondering, this is what we do today. We divide Switzerland into regions, but we wondered, is it actually meaningful to divide something like a railway network into geographical regions and then optimize them? Or could we look at it a bit differently? So if you think about train runs, so if you look at a train running through all of Switzerland, this train will be touched by most operating centers, so it will be organized by many humans. But actually it would not be necessary for a single train to be optimized by many people, so just one could optimize it. Also, if you have a second train that has no interaction whatsoever with this train, there's no need for you to optimize their behavior together. So it doesn't really depend, it doesn't really matter if they're close in physical space if they don't interact. But then if you add more traffic, you realize, well, if a train interacts with both of them, now all 3 of them again have some kind of interaction. So what we realized was train dynamics or train traffic flow on the system depends much more on what trains have some form of interaction, either direct or indirect, during your train run, and not so much on where in Switzerland you are. So we thought, well, maybe the trains should just handle it themselves, and they should communicate and agree on a solution just depending on which trains see each other and which trains have some form of interaction. So this is going away from a network where we had Switzerland as a grid, what we have physically outside, towards a network consisting of trains that are connected to each other through interactions. And the interactions might be, they have to pass through the same train station, or actually the same elements of infrastructure, or it can just be a soft interaction, like passenger actually need to move between those trains. So there's a lot of different influential factors that you have to take into account. And our approach here, coming from using operation centers to optimize, we said, well, let's try to make the trains smart. Let's make them AI agents and see if they can actually collaboratively find a good solution themselves without a central controller looking at the traffic flow. And as you could have guessed, because I'm here speaking at the Reinforcement Learning Meetup, we're going with reinforcement learning as well. I'm not going to explain the whole loop, I'm just maybe explaining what we have done so far. So this nice looking computer game here is actually a high performance simulations we have made. I can show you a video of it. It actually does run on my machine as well, but we run it on a GPU cluster. It simulates all of Swiss train traffic in 3 seconds for 24 hours. So if you want to simulate 1 day of train traffic, it takes us 3 seconds. But if you consider that reinforcement agents usually need thousands of trials, it still takes too long. So we need to make it faster, and I will show you some ideas we had to make it a bit faster in learning. The agent, because we are not a research institute, but rather a public transport company, we are not making research on this part. We are mostly taking state-of-the-art agents and do collaborative work with universities and with Thilo as well, who is also here in the audience today, to figure out how to best solve this part. Then we did some design here on what are the actions you can take, what are the observations an agent has, and then the important part, the reward function, which you heard in the first talk. This is quite complex, and this will change the behavior of your agent, but something which we also realized in our, because it's on a graph and it's a bit more difficult than other problems, that actually the observation part is very difficult as well. And I will come to that in the end and give you some insights into that. So multi-agent reinforcement learning, just brief overview. So what we would have is trains living here, every train being an AI agent or a reinforcement agent. It has some local observation, makes some actions, and this will look something like that. They don't have to take actions at the same time, so it's asynchronous. And the environment will give back some sort of reward from time to time. And this is actually the beauty for us as a railway company, that we can use reward given on the environment state and not on the action, because we actually don't know which actions are good in dispatching, but we do know when our system is good and when it's bad. So if people are on time, we're happy, so we can give good reward. If they're not on time, we're not happy, we give bad reward. You can also enhance this and say we want to minimize for energy consumption. We want the trains to run as smooth as possible, use as little energy as possible. So here we have a lot of leeway. We can play with different parameters to make agents behave differently. And what you need, if you want them to collaborate, they need some form of communication, or they need some form of knowing what are actually the other agents doing. And otherwise you end up with greedy agents who just try to be as fast as possible, but nobody's interested in just some trains, the strongest one being on time and all the other ones being delayed. So somehow they need to collaborate to keep the system stable. What this looks like, we have these different agents and they have local observations, and this is important. This is a huge difference from what you would normally do. So we don't want one single agent to globally see all of the world. This has benefits that if they have some sort of independent local observation, we can compute them independently of all the other agents. And we can actually, I will show you, we can train on local example instead of global examples, which are much faster to simulate. So we have these local observations between the agents and then decide on what they want to communicate. They have a communication protocol where they communicate with the relevant stakeholders. And this is low bandwidth, and this is also ongoing investigation. This is a bottleneck, because this you can do in parallel, this is not possible in parallel, and then the execution of the actions you can do in parallel. So currently the simulation time will stop or slow down the most when you come to the communication part. So somehow communication protocol needs to be fast and simple, in order to, otherwise you lose all the benefits you gain from using multi-agent reinforcement learning. Okay, so I think I can show you the idea that we tested, and then I'll show you some preliminary results and hopefully some live action as well. So using local observations, now you can generate small test examples, and these test examples now just show local situations. You can take some maybe from Zurich, some Bern, and some on the main roads and so on. And these are much smaller, so they're faster to simulate. And now you can train a bunch of agents on different such examples, and you do this. We have actually a DGX1, so we have a GPU, small GPU cluster, where we can train this all in parallel, and then you can kind of use weight sharing and so on. So the agents can actually share their experiences, so you can do some sort of distribution of policies, and you can kind of build a super agent out of that, and then copy that one wherever you like, and then you can test the performance again on the full network. So because simulating this is a bit slower than simulating small parts, we can speed up our learning in this way. So what we have done the last year, I would say, is kind of testing if this actually works. So this was a good idea, but does it actually work? And as you saw in the previous example, it's best to start with a hello world example, not the full dynamic simulation, where you have a lot of stuff that can go wrong. So we did the same. We introduced, okay, so this is the concept we're doing, and we introduced what we call flatland, and that is a simplification of railway dynamics to a simple grid world. And I will come to talk about how we evolved this further and what you can do with it now. So, just simply speaking, on the left you see a train run, and now on the right you see, left is what the real train world is, this is the grid world, and then we simplified it even further, making actions just directional moves or waiting. So we went away from these decisions we had before, which were binary, and we let the agents actually move around freely, and it simplified. The train cannot move like that. The train cannot move back and forth, but for simplicity's sake we allowed all kind of movement, and in further iterations of this environment this is not allowed anymore. And we don't allow for any diagonal movement, and we only allow one train to occupy one cell at a time, so they cannot pass each other. So they have the similarities to railway traffic. They cannot pass, they have targets they have to reach, and they have to organize somehow to get around each other. So an agent would be like this, and then you have to wonder what kind of observation do we give. And in the previous talk we didn't really talk a lot about observation. We saw this 5 or 4 state observation state. Now here it becomes much more complex. So either you just show them an image like that, use some convolutional neural networks to train it on pixels, but it's highly inefficient. And what we tested is, because we are moving on a graph, we cannot move on these tiles anyway, so I'm not interested what's there. So we're just looking along the graphs, along possible paths I can take. So it's kind of performing the observation as a tree search around each agent, and you will see visualizations of this. So that's what we do. The agent can make this observation, it then decides on some action, and the environment executes that action. And from time to time the environment will give back reward, whether the state of the environment is good or bad. So this is what it looks like. A train run on the left is simplified into a movement on the grid on the right. So to test now this workflow from testing locally, going globally, we started like this. We constructed a few very simple examples. And then in these examples, I will show you now, we throw in a few agents, I think it's 3 at a time, and they will be colored with one color, and there will be a tile that has the same color, and their target is reach to that spot and then wait there until everybody has reached their target. When all reach the target and stop, reward of 10 is given, otherwise each time step reward of -1 is given. So this is what it looks like, very non-railway-like behavior, especially during training. You see, this is what training looks like. So trains are very selfish, they stand in way of each other and so on, but over time they start to get better and better. And what we did was really training just always 3 agents on these very small examples. Another interesting part would be, well, does this scale? Do we have to retrain them, or can we just take them and throw them into a bigger world? So that's what we tested. So we constructed a bigger test world here, and now you can throw them in. And what you see here on the right is the agent walking. It's just one agent now, so it's not so interesting. It just needs to find its target. And what you see on the left is what I told you before. This is the observation. So it's making a local tree search around all possible paths and collecting information on that path. So the main information currently being collected is actually, do I see other train stations or stopping points of other agents? Do I see other agents, and so on. So for itself it's not so relevant yet, but when they become more, so let's add, I think it's 15 now, you can see the behavior starts, and you also see we still have trouble, so this is still early research. It's still not converging the way we like, not at all points at least. But you see, when you look at also the tree searches, that you can imagine to get still a global optimal or close to optimal solution, because all the observations of the agents are overlapping, so we at most times will still see the whole world. And actually in the improved version the observation spaces become larger and they're looking much further ahead. And here I would like to highlight something, because this is going to be fun. So we have improved, or we are currently improving on this world to make it more railway-like, so trains will only move forward and not backward anymore. Also the dynamics are not as free anymore, they cannot freely move left or right. There is switches implemented in this grid world now, they can only take whatever the switch allows. And this will be coming soon on AI Crowd, and this will be a reinforcement or multi-agent reinforcement learning challenge, where you can both contribute by finding algorithms that solve this optimally or as good as possible, or you can actually also provide new observations. So the environment is built in that way that you can also build new observations on top of it. So come up with your own ideas, what is relevant for a train to see such that it can optimally find a solution. So this we will be launching as soon as possible. It's in active development right now, and I can show you some preview maybe on that as well. So this will be ongoing for half a year, and our hope is then when we have found better observation spaces and algorithms that solve it better, that we can move back to our high performance simulation that we have built. And now I'm just showing you quickly what that looks like. So this is actually a visualization of the simulation. What you see is the dynamic here is much more complex. So we calculate an approximation of physical dynamics of trains that include weights and the topology. So if the train has to go upward and so on, how much power it has to use. We can also calculate the power consumption of all trains in the system. And what you see from time to time when it changes visualization is local predictions of each train, where it predicts if there will be other oncoming traffic and so on. Yeah, when it squares like that, that's actually local prediction saying, is the path I want to take free and so on. So once on flat land we find good solutions, we want to move them here. And I just want to highlight, so this is one simple example, but because it's on the GPU, we can run hundreds or thousands of them at the same time. If you look closely, you will see they're all different initialization, so there are different number of trains and different schedules running here, and they run at the same speed as if we would run one. So it doesn't really matter if you 1 or 100 or run at the same time. And then we can scale the whole thing up and put our real railway network on, and the hope is then that the algorithms that we have found through challenges and also on these small examples actually solve equivalently well on this world. So that is the hopes. We don't know if that's going to work, but we're very confident, and also on flatland stuff is already looking very good. Okay, so that I was quick enough, hopefully, so we can have beer soon. So this is kind of just a take-home message, and then I'll maybe do a quick demo as well. Especially when you're in industries like we are, and you heard also in road traffic where you cannot experiment on the outside, it's very beneficial to go to simulated worlds. So making, you might call it digital twin or some simulation of your real problem, and then you can use different approaches. And here we use now reinforcement learning, but you can use any kind of algorithm from operations research or deep learning to tackle your problems. And especially you can use this trial and error so you can fail. I mean, if we look at the behavior of the trains in our system, that's a huge failure, but you can learn from those failures, and we can actually simulate terrible situations of railway traffic in here, and we don't have to plague our customers with being part of a game where we try to teach the reinforcement agent to be better. So it's a smart move to go. So if you're interested in any more information, either just email me or Adrian. We are both working on this project. On AICrowd.com, it's one of the featured challenges. It's already uploaded there as a coming soon, so you can read some information. In the coming weeks or month, it should be started maybe in an early beta version. If you are interested, just email me. I can give you beta access as soon as we have it, and then it will launch midsummer, I think, officially. So do you want to take questions now, or should I show you just a little bit?
How long is the show?
I just figured, since I trained the agent on the train here, I figured I can just show a little bit what it looks like. Just small examples here. Actually, and just for the architecture, here we're also using dueling double DQN actually. So this is the environment. It's a bit improved now. It's even further improved. This is not the latest version. Again, you see with one agent, it's quite confident to find the shortest path. That's not so interesting. Here I used 2 agents, I think, when I trained them. So they should be able to work together when they're 2. But that's still quite simple. And the nice thing is, because their observations are local, they're not really aware of how many agents are in the system whatsoever. So I can actually now add more agents. So this was what training looked like when they were by themselves, and then I think up to 6 will probably still work somehow, hopefully. Okay, so now, yeah, we see this kind of behavior sometimes where they cannot agree on solutions, or they get a bit confused at the targets. But from time to time they find solutions. But so this will be a very low baseline. They do find solutions, and here we optimized for a number of solved environments. I could check what the current state is here. Yeah, you can barely see down here. It said it's they solve about 70% currently, and we wanted them to solve all of them, but they're not solving optimal. So in the challenge, even you can get better just by making them smarter and not running around and stopping a bit more often, for example. So the better solution would be that they agree quicker on solutions. And actually, this one is still without communication. We're working on that. So they're kind of selfish. They do have observation of intentions a little bit, but they're a bit greedy. Okay, that's it.
Thank you. Yeah, thanks. It looks like a really fascinating problem to work on. I have a lot of questions, but I'm sure that you guys have maybe even better questions, so let's start. Yeah, in the back.
Thank you for the talk. And my first question is, have you already implemented the communication architecture?
We are working on one. So we have implemented different ideas of broadcasting or messaging boards and so on, or local communication just with agents that you see. But I can't reveal too much what will be in the final version yet. We are still working on that.
So, in an environment that already lacks communication, how are you ensuring a collision-free environment?
Sorry?
So the first point is the trains or whatever the closer trains are locally visible. You're not giving any agent a global
No.
visibility. So how are you ensuring a collision-free environment here?
Here we are not. They can actually collide. They actually get punished when they collide. So they will stop colliding after a while. In the beginning they have a lot of collisions.
So in case...
But in the real world it will not be. So they won't let me plug this into the system, don't worry.
So just to make sure, you had a slide of one of the slides where the agents take decision. The next step is they communicate.
Yeah.
The third step is, I guess, the drivers of the train taking actual decisions, like the human decisions.
Yeah, so okay. Maybe I have to clarify this a bit. This is a bit confusing, yeah. So what we will do, or what the idea is, that you let this run on a simulation, and this is not coupled to the real world. And then you simulate the behavior of this. This would actually be trains, autonomous trains kind of, and you simulate the way they run. And then you look at what switch did they choose, what route and what ordering. And then you send that command to the dispatching, and the dispatching just doesn't run the trains, but it just sets the signalings to get the same ordering as the simulation told. So we use this kind of to predict what will happen, and then we have to translate it again to our real world, because it's going to be a long time till something like that happens. We have to translate what we see in simulations to actual actions of dispatchers in the real world. Yes?
Have you thought about, or do you think it is possible to take into account external factors like weather, or I don't know, the
yes.
tracks being not good enough and then they to slow down?
Yes, we have thought about that, and there is some models on the dynamics of trains on weather. I think the models are not that good yet, but basically we know when it starts raining, in the beginning trains will be slower, they will be delayed, so that we basically know. So we can, and we do have weather data, and we can put that into the simulation, so we could do some broad version of it. But currently what we pursue is that, because we simulate the dynamics of the train, so it has, we look at the physical capacities of the train, so how much power can it deliver, and how much power will go into forward movement. So we have quite a good model of that. And then we just vary the amount of available power statistically, so we make hundreds of simulations and we vary that value. And that effect is larger than the effect of weather. So at the end, we're not interested in one single train run and then take decisions from that, but rather we make hundreds or thousands, and then we get some statistical assumption or statistical values on what should be the statistically seen the best. Still working on this toy example. to show that it works as a concept, and then later on we want to pile on as much information as necessary. Yeah?
So, when you discussed about rewards for the system, you said that they're getting rewards for states, not actions.
Yes.
So when you say states, you say the state a single agent is in, or the state of the entire network?
Entire. So the whole environment as a whole generates the reward. So you have, I would call it like that. So you have the state of the environment that will be coupled to the reward. So the reward is the function of the state. And then we call them observations. So each agent has an observation, which is a partial observation of the full state. Actually, in the challenge, we do allow for full state observation. You can also take all of the information you want. But the problem will be the scalability. You have to somehow efficiently be able to solve a lot of different levels at different sizes. So that's a task that is not so easy with global observations.
So in that case, wouldn't it be, this question would sound very naive to you, wouldn't it be easier because you have high performance machines working on it, wouldn't it be easier to explore the state space of an environment for which you already have an algorithm to give global optimum states than actually going into the direction of multi-agent reinforcement learning and decoupling it to different agents? What I'm trying to say is, so wouldn't, how do you ensure stability? Ensure that maybe some agents would get more reward and that would be globally optimal, and there would be some agents who would be slowed down and pushed down, but the global state would give you more reward altogether, but the people that you have, like people or the trains that have slowed down would be unhappy because of it. But you're still getting a globally optimal solution.
I'm not sure I got the question correctly. What was?
I'm saying, how do you ensure stability between some agents performing really well and some agents performing?
That's actually a hard part. But one thing is, if you only have a global reward, then and they're shared among all the agents, there's no benefit for an agent to be greedy because it will not benefit from that. If they already have it, if one agent is, for example, when you see them in the simple environment, moves as quickly as possible to its target and just stops and blocks all the other train, it will never get any reward. So it has to learn, if I'm the first one to stop, that makes no sense because the reward is coupled to the full environment and not to my own behavior.
So wouldn't it be easier to solve it like as a Monte Carlo research, because you already have an environment that can guess a globally optimal state. So why do we even go into multi-agent reinforcement learning?
The tree is just too big to look at. I mean, Go is peanuts compared to the trees we have. So, I mean, there is solutions. There's actually teams working on solutions like that, where you just span trees and you try to figure out as early which branches you don't need to look at, but they don't scale. I mean, they get up to 80 trains maybe, but then it stops. And usually they do it for planning, so they compute for a few minutes or a few hours, and then they get a plan. But for rescheduling and traffic management, you have to get the decisions in seconds. So we rather not have optimal but feasible solutions, but we want them in a timely manner. So that's the focus is shifted away from optimality towards feasibility and speed.
What kind of system do you have in place in operation right now? Like what do you...
Humans? Humans with predictive systems. So that's what I said maybe briefly in the beginning. We have what's called a rail control system that will make predictions of train traffic given the current situation. So it looks at the signals and where the trains are, and then it predicts the paths, and it will also predict possible conflicts where two trains want to pass at the same place at the same time. And those are then messaged to a dispatcher and he's resolving them. But it's not giving any suggestions about optimality. It's not saying it would be more optimal if you do other decisions. It will just say, if you don't change something, there will be one train will have to stop. And so it's not coupled to safety either. So they cannot collide. So if a human doesn't do anything, the system just puts red lights up and the trains just stop. And you don't want that. So that's why the prediction is telling you if you don't do anything, trains will stop, so you have to. But it doesn't talk about optimality, and that's what we want to improve here, that you get some optimal decisions.
Do you have any details on the algorithm that you use?
This one? So this was just dueling DQN, double DQN actually, with experience replay. Simply, but we're building up the environment to be compatible with RLlib, so you can actually test any kind of algorithm on it. It's very similar to, if you know OpenAI Chim, it's actually what we are hoping to do is the multi-agent version of that. There's more toy examples coming, not just Trailway.
Okay, cool. We can discuss more about beers. So let's thank the speaker. Luckily, we don't have to send you this.
Per email, it's better like.
Yeah, and there's some food and beers. So thanks a lot again to Oracle for providing this. Great to be here. Let's enjoy the drinks.